let's talk about another analytical technique, which is called titration. So in titration, we're taking a solution of accurately known concentration. Oops, let me spell that right. Solution of accurately known concentration and we call this a stock solution. Is added gradually to another solution of unknown concentration. Okay, now if you know the volumes of the standard and the unknown solutions, along with the concentration of the standard solution, you can determine the concentration of the unknown solution. And when we're titrating something, what we're trying to do is reach this thing called the equivalence point. Now, the reason why this is important is that the equivalence point is the point at which the amount of acid has been completely neutralized by the base. So let me write that down. So equivalence point. This is the point at which the acid has been completely neutralized by the base. Now, we know that we've reached the equivalence point because there should be a definite color change in the acid-base indicator. So what we do in order to help us see if we've gotten to this equivalence point is that we add an indicator to our solution. So an indicator, this is a substance that has distinctly different colors in acidic and basic solution. So this is a substance that has distinctly different colors in acidic and basic solutions. All right, now the most common indicator is called phenolphthalein, where it's colorless in acidic solutions, but then when you get to that equivalence point, the solution turns reddish pink. Okay, now we'll try a couple problems out. This is something that I'm introducing now on how to calculate this and all that good stuff. This is something that you will definitely be working with when you take the second semester of general chemistry. All right, so here we go. Let's take a look at this. So the first problem reads this: how many grams of KHP, potassium hydrogen phthalate, and here's the molecular formula, are needed to neutralize 18.64 milliliters of a 0.1004 molar NaOH solution? All right, so let's take a look at how we do this. The first thing we need before we do any math is we got to get a chemical equation. All right, so we know that the acid that we're using is potassium hydrogen phthalate. So let's write that symbol, that compound out. KHC8H4O4. Okay, and this is going to react with NaOH. Now, even though this is more of a complex acid, the H here that I'm underlining, that's the acidic proton. That's the hydrogen that's going to react. So what's going to happen is that this H will react with the OH and displace the sodium. The sodium will take the hydrogen spot. So we should form water, okay, as one product, and then you're going to form the salt, which is going to be KNaC8H4O4. Now, everything is a 1 to 1 to 1 to 1 ratio, so it's all balanced and we're good. So for every 1 mole of acid, you're going to need 1 mole of sodium hydroxide. So it's a 1 to 1 ratio. All right, now at this point, you may be like, hell, I could do a dilution formula and get this. And you probably could. But I'm going to tell you right now that is the wrong way to solve this problem, because that will only work if you've got 1 mole of acid to 1 mole of base. And the problems I will give you on the exam will be different numbers. That won't work. So do not use the dilution formula to help you out in solving this problem. So we got to use dimensional analysis. All right, so we're told you've got 18.64 milliliters of a 0.1004 molar NaOH solution. So that's what we're going to start with. So I'm going to write this 18.64 milliliters. Now, before we even get to the molarity, I got to convert that milliliters to liters. So let's do that real quick. So we know there's 1,000 milliliters in 1 liter. Milliliters cancel out. Now we're in liters. If I multiply this by the molarity, okay, so 0.1004 moles of NaOH over 1 liter, the liters cancel out, and now we have moles, and we can use the chemical equation to convert from moles of NaOH to moles of potassium hydrogen phthalate. So let's try that. So there's going to be, for every 1 mole of NaOH, there's 1 mole of KHP, and I'll shorten it up, KHP. All right, so that way moles of NaOH cancel out. Now we got to go from moles of KHP to the mass, the molar mass of KHP. So to do that, we got to calculate the molar mass of KHP. So 1 mole of KHP, that number I got was 204.22 grams of KHP. All right, so that way moles cancel out. We've got grams of KHP. All right, so this is going to be 18.64 times 0.1004 times 204.22 divided by 1,000. That number I get is 0.3822 grams of KHP. Okay, now for KHP, this is a solid. Usually the acids that we're dealing with are solutions. So let's try another one. Okay, so here's our next question. How many milliliters of a 1.28 molar H2SO4 solution are needed to neutralize 60.2 milliliters of a 0.427 molar KOH solution? Okay, so again, the same thing like we did with the last problem. We got to get a chemical formula before, or a chemical equation before we do anything else. So let's try that out first. So we know we got H2SO4, and we're reacting this with KOH. So the H is going to replace the K. So you're going to get water as one product. And then the other one should be, if the H is replacing the K, that means you should have K2SO4 as the other product. All right, so that being said, if we balance everything out, we need 2 moles of KOH, and we have 2 moles of water, and that should be okay. Everything should be balanced at that point. Yay. Okay, so we're going to set this up just like we did the other problem. So we know that we have 60.2 milliliters of 0.427 molar KOH solution. So let's start with that, 60.2 milliliters. We need to convert this from milliliters to liters first. So there's 1,000 milliliters over 1 liter. Milliliters cancel out, we're in liters. We need to multiply this by the molarity of the KOH solution. So that's 0.427 moles of KOH over 1 liter. Liters cancel out, we're in moles. Now, using the chemical equation, we know that for every 2 moles of KOH, there's 1 mole of H2SO4. So I'm going to use that. So 2 moles on the bottom, 1 mole H2SO4 on the top. So that way moles of KOH cancel out. So now the problem's asking for how many milliliters if we have this molarity, 1.28 molar. All right, so the way I'm going to write this, I'm going to write the definition of the molarity backwards. So I'm going to put the moles on the bottom. So 1.28 moles of H2SO4 goes on the bottom, and I'm going to put 1 liter on the top. So that way moles of H2SO4 cancel out. Finally, it's asking how many milliliters, so we got one more step. So we got to convert that from liters to milliliters. So there's 1,000 milliliters for every 1 liter. So that way liters cancel out. Now what's even nice is that you do have 1,000 on the bottom, all the way the back over there. You have 1,000 on the top, way up front. So these cancel out as well. So math-wise, this is going to be 60.2 times 0.427 divided by the product of 2 times 1.28. And when that happens, the number I get is 10.0 milliliters. Finally, another type of titration that we can go through is an oxidation or redox titration. So the way that we know that we hit the equivalence point is that when the reducing agent is completely oxidized by the oxidizing agent. We can also use a redox indicator to help us when the reaction has reached that equivalence point. Now, the two most common oxidizing agents are going to be potassium permanganate and potassium dichromate. So the presence of one of those two should automatically tell you that that's an oxidizing agent. Now, even though these chemical equations are going to look more complicated and complex, don't worry, because they work the same way as an acid-base titration. You work it out using dimensional analysis. You're just converting from one entity to the other. So let's try this out. So how many milliliters of a 0.206 molar HI solution are needed to reduce 22.5 mils of a 0.374 molar KMNO4 solution according to this equation? 10 moles of HI plus 2 KMNO4 plus 3 moles of H2SO4 yields 5 moles of I2 plus 2 moles of MnSO4 plus K2SO4 plus 8 H2. Holy geez, there's a lot of stuff. Now, like I said, the equation's complicated, but you know that you're working with HI, okay, and you know you're working with KMNO4. So for us, the rest of the equation doesn't matter because we've got the coefficients. We know we're moving from KMNO4 to HI. All right, so you know you got 22 milliliters of a 0.374 molar solution. So let's start there. So let's start with the volume. So you got 22.5 milliliters. Okay. We're going to convert this from milliliters to liters. So there's 1,000 milliliters in 1 liter. Okay. Now let's multiply this by the molarity. So you got 0.374 moles of KMNO4. Okay. Divided by 1 liter. Okay. So liters cancel out. Now, we need to go from moles of KMNO4 to moles of HI, and so we're going to put on the bottom 2 moles of KMNO4 because that's what we're getting from the chemical equation. We've got 10 moles of HI. Okay, so that way moles of KMNO4 cancel out. Now, we're told that we want to find how many milliliters we have. So we need to multiply this by our molarity, okay? But what I'm going to do is switch the definition around. So instead of being moles per liter, I'm going to put liters per mole. So 1 liter over 0.206 moles of HI. Okay, so that way it's moles of HI cancel out. We're left with liters. Now the last thing that we need to do is convert from liters to milliliters. So that'll be 1,000 milliliters over 1 liter. So that way the liters cancel out. So math-wise, and we can also cancel out that 1,000 too. Nice. All right, so math-wise, we got 22.5 times 0.374 times 10 divided by the product of 2 times 0.206, and the number I get is 204 even milliliters.